Hello, I'm Talia Tobias. If you look at the standard mathematical model for a paper glider, it tells you something strange. It suggests that if you fly slow enough, you can hover in the air forever. But anyone who has thrown a real paper plane knows that isn't true. It stalls and nosedives. For my project, I started with the group analysis of the standard glider model, but for my individual extension, I broke it. I identified that the standard math violates physics at low speeds. I'm going to show you how I introduced a deep stall mechanism that doesn't just change the numbers, it fundamentally alters the topology of the phase space, creating a mathematical dead zone where flight becomes impossible. To establish the physical baseline, my group worked with these standard dimensionless equations derived by Blanchard. Crucially, notice that the complex aerodynamics are distilled into a single parameter, d, representing the drag-to-lift ratio. Now, rather than just jumping straight into numerical simulations, we solve this system analytically by setting the derivatives to 0. This plot isn't just a set of data points, it is the locus of equilibria. It proves mathematically that for any given drag profile, the glider has exactly one terminal velocity state. As drag increases, the glider is forced into a steeper dive angle and a lower equilibrium speed to maintain lift. This analytical certainty is the foundation of the standard model. By calculating the Jacobian matrix and analysing the eigenvalues, we confirm these points as stable spiral sinks. This means that in the standard model, the glider always wants to return to a steady, constant velocity glide, naturally dampening out any oscillations. We verified this stability numerically using a fourth-order Runge cutter scheme. Comparing these three plots reveals the fundamental bifurcation in the system, where the qualitative structure of the phase portrait changes abruptly. The top image has zero drag and the system is conservative. Here, the eigenvalues are purely imaginary, resulting in closed orbits and perpetual motion. As soon as we introduce drag, however, the topology changes. The orbits turn into spirals, pulling the glider into that equilibrium that we calculated. As d increases, it deviates more from the closed orbit of d equals 0, which is the bifurcation point. This was a crucial verification step. It confirms our code was accurately capturing the energy dissipation before I attempted to modify the physics. However, during our analysis, I isolated a critical flaw in the standard model. Look at the apex of this blue loop. In the simulation, the glider reaches this point with a velocity significantly below s equals 1. Mathematically, the standard model still predicts a perfect turn because it assumes the lift law, that lift is proportional to speed squared, holds universally, regardless of how slow you go. Physically, this is incorrect. It implies the wing maintains perfect aerodynamic authority even at near zero speeds. In reality, below a critical speed, the angle of attack becomes too steep, the airflow separates from the wing, and lift collapses. The standard model completely ignores this stall phenomenon, effectively allowing paper planes to hover through maneuvers they should not be able to complete. This is the unphysical behavior my extension corrects. To resolve the physical flaw, I introduced a deep stall mechanism. I modified the angular velocity equation by multiplying the lift term by this efficiency function, sigma s. It acts as a continuous aerodynamic switch. When speed is high, sigma is 1. But as speed drops below my critical threshold of s equals 1, the efficiency collapses to 0. However, this mathematical fix created a computational problem. I selected a sharpness parameter of k equals 20 to model the sudden transition from laminar to turbulent flow. If you look at the vector field here, you can see the arrows change direction instantly at the stall line. Mathematically, this is a massive gradient, a cliff in the vector field, which makes the differential equation stiff. Standard time steps failed here, creating artificial oscillations. I performed a sensitivity analysis and refined the time step to 0.01. This ensured the Runge cutter solver remained stable as it navigated the steep aerodynamic transition. The impact of the deep stall mechanism on the phase space is drastic. You can see a clear horizontal barrier at s equals 1. I call this dead zone. Above this line you have normal flight where lift works as expected, but cross that line downwards into the shaded region and lift vanishes. The vector field here is dominated entirely by gravity. This acts as a topological trap. Trajectories can dive into the stall, as shown by the red line, but they cannot orbit back out without first diving to recover speed. Unlike the standard model, sustained loops are mathematically impossible in this region. Here we see a high-speed launch at s0 equals 3.2. Notice that on the way up, the red and blue lines are identical. This is physically correct. At high speeds, the stall mechanism is inactive, and my model matches the standard aerodynamics perfectly. But right here at the apex, the speed drops below my critical threshold of s equals 1. This is where the physics diverge. The standard model, blue, assumes perfect lift and pulls a tight turn close to the loop. But in the deep stall model, red, lift collapses. The glider loses aerodynamic authority and cannot hold the turn radius. Instead, it mushes downwards, slipping out of the loop. I quantified this failure energetically. The stall model loses 25.8% of its total energy, compared to only 0.4% in the standard model. This confirms that stall is a hysteretic process. The potential energy lost during that downward mush is irretrievable, making the maneuver mathematically impossible to complete. In conclusion, while our group project successfully categorized standard flight stability, My extension demonstrated that adding non-linear stall doesn't just tweak the numbers, it fundamentally alters the global phase space topology. It introduces a dead zone, enforces realistic energy hysteresis, and eliminates the unphysical hovering loops found in the standard model. This confirms that incorporating non-smooth aerodynamic effects is essential to capturing the true and often dangerous dynamics of flight. Future work could quantify the recovery envelopes, calculating exactly how much energy a pilot needs to escape this dead zone. Thank you for listening.